Swayam Prabha. Digital India. Educated India.
Now, the constellation is developed okay. The constellation tells us how the material responds, it tells us how the material responds. Material response. So, basically we saw that the stress and strain are concepts introduced to lose the geometric dependence, and constellation is a material dependent relationship wherein you know that the steel responds differently from a rubber bar, right. So, that material dependence is brought in by the constellation. Okay. In the constellation you have various class of constellation called as elastic constellation, plastic constellation, viscoelastic constellations and viscoplastic constellations, depending upon how the stress, the kinetic quantity and the strain, a kinematic quantity are related. Okay. The stress and strain can be related directly, or stress rate, strain and strain rate can be related, or there are different ways by which the relationship can be proposed. Depending upon that, it will fall into the metal being either elastic or plastic or viscoelastic or viscoplastic. In this course we will be interested only in the elastic response of the material. So, let us understand what we mean by elastic. Okay. Elastic response. A textbook definition of elastic response is: if I load a bar in uniaxial tension and let go the force, it should come back to its original state, right. If I pull a bar and let the force go, it will come back to its original state. That is a definition of a elastic response. Okay. That is, if I pull a bar, it elongates to this shape maybe, and when I let it go, it comes back to its original shape. Okay. So, that is a definition of elastic response. In other words, what we are saying here is there is no dissipation. Elastic response means there is no conversion of mechanical energy to thermal or other forms of energy. Okay. So, essentially what we are saying is the mechanical energy will be stored in the body as a mechanical energy and will be released from the body as mechanical energy when you remove the load. This is called as no dissipation condition. That is, if I load a bar, say this is a loading part, if I unload it from here, it will traverse the same path again, it will won't do this. If the unloading is like this, okay, even though it reaches the same state, this is not elastic, this is not elastic. Okay. The loading and unloading path have to be the same, the shape should be preserved. So, all these are the attributes of an elastic response. Okay. Now, we will be interested only in this elastic response of the body, and hence we will relate the stress directly as a function of the deformation gradient F. Okay. since we are interested in only elastic response, we will say that the stress is a function of the deformation gradient f. Okay. Now what happens? Now there are certain requirements of this constitutive relation. One is it should satisfy second law of thermodynamics. Two is it should satisfy restriction due to objectivity. What does the second restriction mean is, it does not matter whether you do an experiment in India or whether you do an experiment in America or whether you do an experiment on the surface of moon or you do an experiment on Mars, the constitution that you infer for a given material should be independent of where you do the experiment. Okay. That is the restriction due to objectivity. Irrespective of where you do the experiment, the constellation for a given material will not change. Okay. In other words, what it means is, when you place the body in the Euclidean space, each of us can place the body in a different region. Okay. This is a body, I can place it here, I can have my coordinate system oriented like this, oriented like this, oriented like this, it can be here, it can be there, anywhere it can be, but this body's constellation should not depend upon any of these placement of the position vector or how I represent the body and its surroundings in a Euclidean point space. Okay. So that is what a restriction due to objectivity means. The restriction due to objectivity means anywhere you do the experiment, the constellation of the body should be the same. Okay. So based on this, you will find that to satisfy these two restrictions, you will find that the most general expression for the stress would be equation of this form, alpha 2 B inverse, where alpha I is some function of trace of B, trace of B inverse and determinant of B. Okay. Now B is F transpose. Okay. This is called as the left Cauchy Green deformation tensor. Okay. B is called as a left Cauchy Green deformation tensor. It is F times F transpose, where F is the deformation gradient that we have seen before. Okay. Now just like we computed C in terms of epsilon, the right Cauchy Green deformation tensor, let us compute what is B in terms of the displacement gradient. You know that F is related to the displacement gradient as 1 plus H, this will be 1 plus H transpose, this is 1 plus H plus H transpose plus H transpose. Again, if this will be 1 plus 2 epsilon if components of H is of the order 10 power minus 3. What I have done, I have neglected this term H transpose, saying this is of order 10 power minus 6. So I have neglected this and I have written this as 1 plus 2 epsilon. Okay. Similarly, I can find B inverse would be 1 minus 2 times epsilon. Okay. I will not go into a detailed derivation of this. B inverse would be this, then substituting these two expressions for B and B inverse in this expression for stress, what you will get is you will get sigma to be alpha naught plus alpha 1 minus alpha 2 times identity plus alpha 1 minus alpha 2 times epsilon. Okay. So, what you have done is this alpha i's would be function of trace of B, that will be 3 plus 2 times trace epsilon, this will be 3 minus 2 times trace epsilon, that is B inverse, and determinant of B can be shown be 1 plus trace of epsilon. Okay. This is nothing but determinant of B. I am not interested in deriving this, I am just interested to show you that how you obtain one of the constellation that will be using in this course, or the only constellation that will be using in this course, that is Hooke's law. Okay. So, basically what you find from here is this alpha I is all functions of trace epsilon. So, alpha I is a function of trace of epsilon. Okay. Since we neglected higher order terms of the displacement gradient, this alpha naught plus alpha 1 minus alpha 2 and alpha 1 minus alpha 2 cannot depend upon higher order terms of the epsilon. So, even though this is function of trace epsilon, this can be at most mu I plus lambda I trace of epsilon. It can be at most functions of this linear functions. Let us substitute that in here. So, what will I get? I will get sum of linear functions. So, it will be mu I plus lambda I trace epsilon times identity plus 2 times, let me say mu 0 lambda 0 mu 1 plus lambda 1 trace of epsilon epsilon. Okay. Okay. Now, what happens when this is the stress? When strain is 0, what should be the stress? The stress has to be 0, right? When there is no strain, the stress has to be 0, which will imply that mu 0 has to be 0, because trace of 0 is 0, these terms will vanish, this and this entire term will vanish, I will have mu 0 identity, which means that mu 0 has to be 0. Okay. Now, then I have here trace epsilon times epsilon, that is a nonlinear terms, it will have gradient of h components which are squared, right, because trace of epsilon is epsilon xx plus epsilon yy plus epsilon zz, which is dou ux by dou x plus dou uy by dou y plus dou uz by dou z. Okay. This multiplied by epsilon, trace epsilon multiplied by epsilon would be of order 10 power minus 6. Okay. Since I ignored this order before, I have to ignore these terms also. Okay. So, you get finally the stress to be given by lambda naught trace epsilon identity plus 2 mu 1 epsilon. Okay. I will drop this suffix, and simply write sigma as lambda trace epsilon identity plus 2 mu epsilon, where this lambda and mu are material parameters. In particular, it is called as Lamé constant. Okay. So, this is a constellation that we will be using in this course. Okay. In the next class, we will see how to estimate these material parameters, and then we will dwell more into these constellations. So, in this lecture we looked at the two remaining equations that we haven't looked at till now. The in this lecture we have looked at two equations that we haven't looked till now, the compatibility condition and the constitutive relations. Okay. In the previous lectures we looked at all the four concepts: force, displacement, stress and strain, and we looked at equilibrium equations and strain displacement relationship. In this lecture we have looked at what compatibility conditions are and what the constitutive relation is. So, this completes basically the four concepts and four equations that connect them in mechanics, used in mechanics. Okay, thank you.